Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am very happy to have Ramses Ramirez with us today. Hello, Ramses.
Hello, Frank. Hello, everyone. It's a pleasure to be here to talk about my work.
Absolutely. It's a wonderful, wonderful article, and we're going to get to that. Ramses, where are you located at?
Well, it's a little bit colder now these days. Contrary to popular belief, it does get cold a little bit in Florida and Orlando. So that's
Florida.
where I'm at. Yes. So it's not as cold as the rest of the country, most of the rest of the country, but it does get, we do get, 5 degrees Celsius or something like that during the winter time, even a little bit lower.
You're more in the middle of the state, right? You're not down by Key West or something, right?
No. So we're subtropical here still. So we do still get a little bit of chill in the winter. It's not like Miami or the Caribbean where, their winters are quite a bit warmer.
Yeah. Cool. Very cool. So it is January 19th, 2024 as we record this. I'm in Phoenix. Phoenix is in its winter mode. So winter mode means we will go just above, a little bit above freezing of water in the morning. And then by the afternoon, it will warm up to be very pleasant. Very cool. And Ramses, what do you like to do for research?
Well, I am a few things. I planetary scientist, planetary astrophysicist, atmospheric scientist, and astrobiologist. I think I can go by any of those. And what I do is I model and I develop models, atmospheric models of all types, climate models, atmospheric escape models to simulate the climates of planets in our solar system and beyond, specifically trying to address the age-old question, why are we here? Are we alone in the universe? Is there ET somewhere else? So that all my work is on from an astrobiological bent. I do all my analyses trying to answer this question, questions such as what makes our planet habitable, what made early Mars habitable. It looks like when we look at the geologic evidence, or at least more habitable than it is today.
Right.
I mean, 4 billion years ago, it was a very, you look at the geologic terrains, it was, you can see it's just littered with ancient river valley features and fluvial networks and even possibly ocean shorelines. So something happened in the middle and so it looks like it had a thicker atmosphere and possibly warm enough to support liquid water. And so trying to understand that, what happened there. Venus, what happened to it? Why is it not more like the Earth? It probably underwent some runaway greenhouse that removed a lot of its water. And then from an exoplanet perspective, I take some of these, the same sorts of questions, except trying to understand exoplanet habitability. So I help the astronomers stay honest in their observations, right? So they'll find planets and they'll ask someone like me to try to discern or infer some sort of atmosphere for it, whether it's a potential candidate for follow-up observations for habitability, if there's the possibility that an ocean can exist on that world, if so for biosignature studies and things like that. A lot of that work I've helped develop much of the improve the habitable zone, basically. This concept that we've been using for the past few decades that missions use to find planets located in that region. I was one of the main authors there, main co-authors to develop that concept, which I then have subsequently expanded to include other gases, to assess the temporal evolution of the habitable zone. And so, I do a lot of things, but all these aspects, both in our solar system and beyond, is all trying to answer these questions about, are we alone in the universe? That's essentially what my work is all about. And at least that's what drives me.
Cool. Very nice. Thank you. That was awesome. And one of the common characteristics of those objects you mentioned is they all rotate. And I think that is going to bring us to this very lovely PSJ article. It is open access. It's the open access era, people. Go ahead and grab a copy, get one for free. A new 2D energy balance model for simulating the climates of rapidly and slowly rotating terrestrial planets. And Ramses, take us away.
It's my pleasure. So this is essentially something I had been thinking about for years. Ever since I finished my PhD, about almost 10 years ago now. And
Time
yeah,
flies.
it does fly. It's amazing. Lots of things have happened since then. And this was around the same time that about 2013, 2014, when 3D GCMs got very popular. And trying to people using them to try to simulate the climates of planets, of exoplanets. So they're traditionally used to simulate the Earth, right? And maybe present Mars. But then about a decade or so ago, following the publication of our 2013 habitable zone paper, then people got the idea, hey, let's do this in 3D. Right. And so there've been a slew of papers for a few years after that, people trying to calculate the new edges of the habitable zone and using a 3D model, how that compares to 1D, and in some cases they agree. And I think overall it does agree. I think there's still some, no one's done those calculations in high temp. So, I mean, if any 3D GCM modelers should do that calculation in high temp, it's more accurate. I think you'll find the 1D and 3D models will be in complete agreement, very close when we wait for the inner edge. But that's another topic for another day. The issue here is that for me, and basically looking at these models, 1D and 3D models, they have lots of advantages and disadvantages. So if you're using like a simpler 1D model, they're powerful. They don't have all the complexity of a 3D GCM, but they're pretty good for what they do, and they can simulate large portions of parameter space. They can explore parameter space very, very well because they're not as cumbersome. They're not as computationally expensive.
Right. Even when you have a relatively large chemical network within the simulation.
Exactly. That's exactly the point. That's exactly right, Frank. So you can actually do more chemistry with a 1D model.
Right.
You can put in more compounds because you have that computational, it's computationally cheap to do so. Whereas this is more limiting in a 3D GCM. So whereas a 3D GCM, if you know the planet well and you have enough observations ahead of time, you can do a darn good job, like getting a lot of detail in addition to what a 1D model can give. So like information about the circulation patterns and whatnot. And
they're complementary.
They're complementary. The other thing that a 1D model can't do is, it's not really that good. I mean, there is a trick. I mean, there is a way to use a 1D model by changing the coordinate, doing a coordinate transformation to get it to simulate tidally locked planets. But they're mostly used almost always. They've been used to do rapid rotators. But you can do it with a tidally locked planet, doing some funky transformation, but it is not many models do that. But even those that can, you still don't have the longitudinal information that you can get from, say, a 2D model like the one I've developed. So, I mean, I've been looking at the pros and cons of 1D and 3D models, and, I like, okay, you have, I wanted something that can get some of that complexity from a 3D model, additional complexity and ability, and still retain the ease of use and simplicity and quickness of a simpler model. So I wanted to marry both of those.
Cool.
And that was really something that had been kind of bubbling up inside me for years. I'm like, well, I don't think I want to go to 3D route because that would really put a crimp in my research. I think I would have to completely I like to look at a lot of parameter space, look at a lot of different types of planets, and I felt with 3D it was very limiting. I mean, they're very, very good at like specific planets and specific worlds that we know about. But I wasn't satisfied with that. So,
Right.
but I also wanted more of the detail and complexity of the 3D model. So I had developed first a 1D model. This
Always.
was a 1D latitudinal model. So this is an EBM, an energy balance model. So I started with a radiative convective climate model. That's what was used to model the habitable zone in our 2013 paper and my early Mars work and all this. Lots of papers I've done with that model from my PhD advisor, Jim Casting's models. But then I developed then subsequently in 2018 a paper that we published. Yeah, exactly. Ramirez and Levy right there.
Yeah.
The Ramirez and Levy 2018. So right down the bottom of that page, the top of the second page, right? That.
Oh, there we go.
Right.
Sorry.
Yeah, it's right there. Yeah, I just you found it, so that's good. So Ramirez and Levy 2018 was the 1D latitudinal energy balance model that I developed for this paper, which combined geophysics and climate to model ocean worlds with high pressure ices, and that's a complicated topic. But this was something that I was finally able to do things I couldn't do in the radiative convective 1D model, like taking into account rotation, eccentricity, and obliquity, and all these things that you can do in a 3D GCM. And it was to me, it was a nice upgrade. I could then start looking at some problems I wasn't able to do before. I was able to then finally start looking at, at least planets that can rotate quickly and slowly. And so, but without it was still fast without it being encumbered by a computational expense. So this was a big thing that I thought that was very good in 2018.
Cool.
And then it wasn't until and I've written several papers with this model as well, including the other Bonatti and Ramirez 2021 that you have highlighted there. This was also using that same model from 2018, that 1D energy balance model that again does the latitudinal banding. So no more, not just a globally average temperature as you would in a radiative convective climate model, but a full, like at least latitudinal dependence now.
Right.
So like I say, you could do obliquity, eccentricity, all these things. And so I wrote some nice papers on that, using that model, several of them, even redoing the habitable zone, looking at the effects of pressure in 2020 and looking at the complex life habitable zone also, I think, in that year as well, using this model. So I did a lot with that 1D EBM.
Awesome.
And but I was still not completely satisfied because I wanted a solution that could properly do tidally locked worlds and rapidly rotating planets and really have the full picture, like of the surface distribution of temperatures and pressures, as well as the top of atmosphere information you get from these models. You don't get zero vertical information. You still get, even from an EBM, a 1D EBM, you do have some vertical information like the planetary albedo. You can do that as a function of latitude and things like that. And the fluxes, outgoing emission and things like that. But the next logical step was taking it to 2D, because I wanted to show that, because the big thing also was like, I was also kind of a bit of pride too, I have to admit. You keep reading papers, how 3D models can do this and 1D models cannot, and you need to do everything in 3D because that's the way you model a planet. All these things, I never quite agreed with that because they had so many parameterizations based on Earth that doubtful that you could really apply to exoplanets with our current knowledge. I think there was still a lot of room for simpler models to do comparable, calculations of similar quality without taking as much time. So it wasn't until the paper by Okuya et al. 2019 That was what I needed. I'm like, I wanted this was to me is a classic. I really respect the work they did. And I, it just kind of fell under the radar. I was surprised that this paper did not get more attention than it did, because
late
it's
bloomer, maybe
really,
a late bloomer.
yeah. I mean, they're Japanese, and maybe I don't think maybe they publicize their work very much from to a Western audience, right? Europe and the U.S. But this was the first bona fide 2D exoplanetary EBM.
Cool.
Like, so there had been 2D EBMs, created for the Earth and things like that, but this is the first actual planetary exoplanetary 2D EBM developed based. They took took a page from earlier works, but this is the EBM, like the Northern Coakley, exactly, the Northern Coakley and Pollard works. So these were some of the stepping stones that they stood on to create their model. And this is what really inspired me. When I saw this paper and read it, I'm like, wow, so this is possible. You can have a fast and nice complex model at the same time that can do a reasonable job simulating atmospheres. And I guess my framework for determining, how good a model is can it match observations? Can it can it produce results that are consistent, at least within the spread of GCMs as well, which is something I also show here in this work. So and we'll talk about that in a second. But this was the paper, I mean, that really just, and it's the funny thing is that I was in Japan at the time.
Yeah.
And that was my kind of like a research scientist position before I became a professor here at University of Central Florida. It turned out that my colleagues there were working on this model. I just happened to be there, and I heard about it, and I congratulated them. I was completely amazed by this. I'm like, this is great. This is exactly what we need to push this forward. And so I just took it upon myself. Then I started working on it slowly. COVID hit, right after that. And then, things kind of slowed down. And then I eventually got hired here and moved and had to move
Life
back
happens.
Life happens. All this, so I didn't get that much done in 2021 on this, but then I hit it hard the past year and a half and got it, finished, late last year. And so this 2D model is great. I mean, I think it is, at least. It's the first 2D planetary EBM that can simulate both rapidly and slowly rotating terrestrial planets and exoplanets with these. And so these are very common atmospheres in exoplanet modeling. So N2 CO2 water, and also hydrogen, if you care about the protoplanetary disk and hydrogen accretion. And this model can do that. So it can be used to model, say, magma oceans and things like that in early primordial atmospheres orbiting main sequence stars. And so it can, you can even add topography to it if you wish. So admittedly, that part of it is crude, but you can make it as detailed as you want, because the longitudinal grid is also as complex or as simple as you want to make it.
Fair enough. Okay. All right.
So you can add those formulations. And in this paper, I did a simple one for Mars topography, just simulating the major mountains there, the Tharsis region and the highlands and the lowlands. So I was able to showcase that you got results that were consistent with other 1D and 3D models, as I'll talk about in a second. But this model was it. And so if we look at, say, equation 1, This is the basic, this is the basic energy balance equation. It looks a little bit like the base equation that you would see in a 1D EBM. So this basically just says that, energy is basically in radiative equilibrium.
Right.
The incoming flux is balanced by all these different factors, including there's so heat is assumed to be transferred through diffusion in these models, typically in an energy balance model. In reality, it's advection that does the transfer, but diffusion is an extremely good, has been shown many times that it's a very good approximation, and it's simpler to deal with.
Yes.
So the subscripts, so D1 and D2, these are like some diffusion coefficients that are pre-calculated. So this is also another first in this model, that a lot of the time a lot of these constants are kind of fudged, or you modify them depending on the case, right? But these are actually being self-consistently computed based on some other assumptions, like the ones here, like equation 2 and 3. And so this is great.
Okay.
And the 1 and the 2 here, these are these subscripts. They refer to, pretty cool, to the latitude and longitude respectively.
Right.
And so in a normal 1D EBM, you just have one diffusion coefficient, and that you assume that the energy is just being transported, just latitudinally, and that's that. But here you have the longitudinal component, so we can. This is one of the major secrets to getting the tidally locked planets correctly as well. They're similar in form, except for the rotation rate aspect. So this is just to show that as you like in latitude space, if you increase the rotation rate, you make it go faster and faster, than those zonal jets increase. But if you slow it down, then you're upping, the Hadley cells are getting bigger, and that transport towards that meridional transport intensifies. And so these equations are meant to capture that behavior. So they're similar, but they're slightly different in that sense. This is kind of similar, like the 1D formulations. If you look at say Williams and Casting 1997, that's where they had a similar form, sort of like they had some of the terms. I added some new ones. And Bonatti and Ramirez 2021 with my student at the time, we added kind of this water component that you see there. A slightly different version of this, but the initial version of the Williamson casting assumes that the planets don't have a lot of water vapor, but to properly get the transport, you need to, especially go to higher temperatures, you need to calculate that self-consistently. And the nature here, the way it's done here, is that it follows Clausius-Clapeyron. So I believe it's Rosen and Langen. I forget the year, but they showed that the Clausius-Clapeyron is very important to the transport. So I captured that in here, as well as the rotation rates that and whatnot, and the difference between latitudinal and longitudinal transport is all being accounted for. And so, so this is just more discussion about the differences between the latitudinal and longitudinal transport. So, and then these formulations. So if we go up, I guess what's that, equation 7, I believe.
Okay.
Or that's or further up. Yeah, 7, I think. So it can do cloud coverage. So there's some GCM parameterization I use for cloud coverage, which is pretty good, I think. And we can go further down.
8 and 9.
And
then we have greenhouse.
We have some. Okay, so the equation 4 is just you can do a curve fit for the diffusion coefficient based on the rotation rate, and there's more details of this in the appendix. But the one of the key equations here, the solar flux equation. So I have actually two slightly different equations. This is the other key factor for the differences between rapidly and slowly rotating planets. So I have one form of the equation for rapidly rotating planets. And another form, if I scroll down a little bit more, so equation 6 is that's the other form for the other planets, so tightly locked planets, for instance. So this is it's a function of the latitude and longitude again, but this gets, what this does is that it does the proper transport for these types of planets, and you get a true substellar point, and and a day side and a night side. This is part of the reason. So this is something that Okuya et al., this was the missing ingredient I was missing when I was thinking about these models in the past, and Okuya et al. 2019 had put in their model. So I adapted their formalism.
Sure.
And so, in addition to also being able to model these rapidly rotating planets. So this is one of the key things that differentiates this model from, say, 1D EBMs or radiative convective models. Is
what happens at intermediate rotation rates?
Yeah, so that's a good point. So I guess so what do we do here for the appendix explains the actual range of rotation rates we looked at, and let me just
we'll save it.
Okay, but essentially it does go over I think it's like it's either 2 or 4 times as fast as the day, and like one up down to about 1 let's see 0.05.
We'll save it.
So you can go to much lower, like 1/20th the rotation rate, and like 2 or 4 times, I forget, it goes over that range. This just what it's been parameterized to do, based also on so this is actually the parameterization is almost completely, so it's not me fitting anything either. The coefficients I use for this parameterization that I discuss in the appendix for getting the diffusion coefficient self-consistently, it's mostly, I mean, I compared against 3D models as well, but it's mostly just predicted model behavior. It's what I needed to get to convergence. It was so cool. Once I got the physics in there, I was able to self-consistently get the right coefficients for different rotation rates. And so, and we can show that. I mean, we can show that now, actually. Actually, that figure 11 is good for mentioning this point. So if we go towards the end of the article, but not before
I love it. There we go.
So before the appendix. So this one here, I'm just comparing against another 3D GCM, the Caspian Showman 2015. And this is a track of the equator to pole temperature gradients. So I have, again, I have a much simpler, faster model, right? They have the 3D GCM. And the equator to pole temperature gradients are pretty similar. In fact, there's even bigger disagreement across GCMs. Like if you look at the high and low end ranges, I'm definitely right. What you would expect a 3D GCM to get. So we looked at, so I think over here also answers that question about the rotation rates that I looked at. So it is,
matching
like 1/20th to, what is it, 4 times the rotation rate of the Earth. So I looked at this range and got very similar gradients between equator to pole between the 3D GCM and this 2D model. Which, again, I have to reiterate the importance of this is that a model such as this, I can get a simulation, run a simulation, get done literally in seconds, right? I can actually get a converged solution in seconds. Whereas a 3D GCM doing the same calculation could technically take days to do the same thing. So it is a huge increase in the amount you can actually, do a lot more calculations and look at a lot more parameter space and get results that are at least believable, right? So based on our current scientific knowledge, we can get results that are believable. So
okay,
now
let's take a look at figure 1 on some of those results.
Yeah, sure. So figure 1 here looks at the
Earth.
it's like, can we we can't zoom out a little bit, or no?
I think that's on your side. It's on full zoom my side. I have a full page up.
Oh, okay. So maybe
you need to adjust your view.
Yes. Okay. Thank you. So so I'm looking at this plot here. So here's figure 1, and this is just a test case for the Earth. Just to make sure things are working. And so remember, so Earth is a rapidly rotating world. Yeah. It's rapidly rotating. So you're not going to get this like eyeball substellar point that you would with a tidally locked planet, and it has this banded structure that you actually would see on the real Earth, this banded temperature structure, because you have the longitudinal transport that transports that energy across different longitudes, and so and latitudes, well, right? But the more insulation, obviously at lower obliquities or lower latitudes, and it gets colder at higher. But I'm showing not just the surface temperature here, but the thermal emission or the outgoing long wave radiation and the planetary albedo as a function of latitude. And all these, when we do the averaging, you get the 288K surface temperature, which is the mean temperature for the Earth, as well as the appropriate OLR, or the outgoing long wave radiation, of 238 watts per meter squared, and a planetary albedo of 0.3. So when you average out these albedo values, for instance, over and all these values, surface temperature, thermal emission over latitude and longitude, they will produce this average result that we have in the caption for figure 1. And this was done so for a Earth-like CO2 composition, so like 1980, circa 1980 CO2 levels, somewhere like that. Just because that number keeps increasing every year, so. But just to standardize it, we typically
at least some baseline value,
some baseline value, 330 ppm, and this result's pretty consistent with what other models get or should be getting for these conditions. So at least gave me confidence right away that at least for the Earth it's working.
Yeah, very nice.
So
very nice. Good.
And then here is just some simulation inputs for the model. So like latent heat of condensation and wind speeds and relative humidity. And we looked at a few different surface relative humidity. So we assume different amounts of surface water, basically, or wetness of the surface. And the rotation, the knot values for CP, P, rotate omega and M. These are like the heat capacity, pressure, rotation rate, and molecular mass assumed for Earth conditions. Those are the baseline values for Earth. But then we calculate these self-consistently for planets that are not Earth. Right. So these are just some inputs that the model needs to run. And aside from those inputs, then it just runs. So and of course the equations. So then those results that we just showed for the Earth, that's under the rapidly rotating planets regime that we looked at. So the
yes. Okay.
So yeah, in this calculation also, I assumed flat topography,
Yeah.
but I include topography in the Mars case. So that's the following set of plots, I believe, the next
This is
couple.
for early Mars, yes.
Yeah, so this is not just
Faint young sun.
this is now the faint young sun problem for Mars.
Uh-huh.
And so when we look at, say, what is this? Figure 2.
Uh-huh. Figure two.
Again, this is for Mars, and assuming a 95% CO2, 5% hydrogen atmosphere. So this is like trying to warm Mars, and you get some surface temperature that's around 280K. So that's pretty warm with its own outgoing long wave radiation and albedo. And so
Yes. Okay.
and here we assume what so yeah, this contains an ocean, this particular case in case 2, in the northern hemisphere and in a sea Hellas basin. So the heterogeneity that you see is due to like competing heat and moisture transfer between those water sources and things like that. But again, these numbers are very consistent with for this case what other models get for these set of conditions.
Nice. Okay.
And then that's so relatively flat topography case as well. But then we go into the topography case here. This is just a quick and dirty
early Mars
simulation for early Mars. Again, we added the like a very crude representation. This is, I guess, the most crude part of the model at this point, because I just wanted to show that, that you can put topography. But basically, it's like a square volcano, and just one. The Southern Highlands is just one big one big bulge on the that southern half of the planet is just elevated with respect to the northern half. So it's very simplified. And the Hellas Basin region, so that's the other circle in the bottom, that's there as well. And there's some heterogeneities that come from the topographical influences that affects the albedo a little bit. And so this also showed results that seemed pretty consistent. Now the what's interesting is that the topography didn't have a huge effect on the temperatures and overall results with respect to the no topography Mars case. And this is actually consistent with 3D GCMs are getting the same thing. So I want to say it's Scott Gusewicz's paper from 2021. They did, for Mars simulations, they did early Mars, both with and without topography, and they got, the very similar results between the two within a couple of degrees mean surface temperature. Good. And that's also what I get here. So again, this is very promising that it's a 280-ish. I think 281K was the mean surface temperature of the flat topography case for early Mars, and then with topography, it's 284. So it's again, topography didn't have a huge effect on the overall temperature. So that also was nice to show that.
Nice.
And then after these, so that was the rapidly rotating planets, right? And then we get into, I guess, the Tally-Lock, or I guess, if you want to be more correct, synchronously rotating worlds. So that's what these next this next set of plots represents. So
we got the eye. Okay, here we go.
Now you get now you got a completely different regime whereas you got this nice banded structure for Earth and Mars. You have this different situation here. So this is this figure. What is this? Figure 4, I believe.
Figure 4 for TRAPPIST.
For TRAPPIST-1. So this was TRAPPIST-1 is started out as this is part of the TIE intercomparison project that this is the reason why I submitted to to this journal, to PSJ, was to enter that special edition and kind of share my results and compare them against 3D results, and
Good.
just have them in that. And so so this paper is also additionally in the TIE special edition. TIE is the TRAPPIST-1 habitable atmospheric intercomparison project, I
Very
believe.
good.
And so it's the purpose of that intercomparison is for different models to assessing different atmospheric conditions for TRAPPIST-1E, and sharing and seeing and comparing, contrasting against models. What results do you get if you vary the atmospheric conditions in TRAPPIST-1E, change this CO2 pressure, and so on and so forth. So I decided to get involved in that project, and so that's what these next results are. Was my contribution to what my model gets when I do the similar model ensemble runs that they did. And so, as Frank said, you get the nice eye in the middle, that substellar point region. So that's consistent with the day side. And you start seeing, okay, like the cooler night side region. And the upward stellar flux plot is interesting because it shows, that there's no stellar flux in the night side. It's zero. It's because there's no sunlight there. And all the energy is being reflected on the day side. But you do get this nice transport. You get not much here in this particular case. I think this is the cold, 235 K.
Yeah.
So you're seeing that the night side's still pretty cold. The night side, so between beyond the day side points, outside of the substellar region. The blue is the night side basically in here, because there's not a lot of transport at those temperatures, so it stays cold. But so this is what this shows here. And it shows that you're able to do this slowly rotating regime as well. We can go on to the next figure.
Okay.
So I guess, I want to also say, I forget. So for another reason why this is cold is because for figure 4 and figure 5 is that we're looking at a dry TRAPPIST-1. Okay. So it has an Earth-like 400 ppm CO2 in this simulation, figure 4, but it's there's no water vapor, so we're just looking at a dry, like a dune-like planet. And so again, that's another reason why there's not a lot of transport or anything going on, not much of anything going on in the night side. And then figure 5 is we increase the CO2, or I increase the CO2 to 1 bar. And again, these were the benchmark cases for the TIE project. So for figure 4, that was the benchmark 1. I should mention that was the benchmark 1 case for TIE. Figure 5 is benchmark 2. And so this one was the 1 bar CO2 case, and it shows it's a warmer atmosphere. So it goes up to 262 K. It's still pretty frigid. That's below the freezing point, but it's starting to get warmer, at least the day side. There's not that much transport yet. It's still pretty cold. Again, you don't have the benefit of the water vapor to transport moisture. And then we go into the habitable cases for TRAPPIST-1. That's figure 6 and 7. So figure 6. Then we start seeing interesting stuff happening. Starting to a little bit. It's still cold. I mean, this is 400 ppm of CO2. This is not the high CO2 case, but we are starting to see some more transport already, even though it's cold. A little bit of the hint of like a little bit lighter blue on the night side. You're starting to get some activity there, some transport. And for this case, it's 250 K mean surface temperature, so it's still cold, but you're starting to get transport.
Here's 6. Let's go to 7 to compare.
And then 7, 7 gets
CO2
even
aqua habitable case.
This is the habitable case 2. you get up to 282 surface temperature. And so in this problem or this case, actually, the scale is different here.
Yes.
The blue is much warmer in this graph. So it's 260 is dark blue. So this is a much warmer.
Right.
My color scheme is not consistent among the graphs, I believe.
It's fine. But you're saying the scale. That's fine.
But it's to scale. So you can see that you can look at these temperatures when you compare to the previous plots that are much colder, like 190, 170 for the night side. Now you're getting to 260s and 270s on the night side. And that's because you have, more transport from the day to the night side. You're trying to really warm that night side up. Of course, the substellar region is the warmest, right? And the point right at the center is the warmest. These are, by the way, these are all, I'm assuming no obliquity. These are exactly 0 degrees obliquity.
Okay, that's fine.
No tilt. But the stellar flux, again, it shows in spite of not having any, stellar flux arriving, if you look at the upward stellar flux plot, there's no flux at all. There's no starlight hitting the night side on this world, and yet it's starting to get warm in that night side,
right?
For this 1 bar CO2 atmosphere, again, because of the transport of energy from the day to the night. So that's really interesting. And then I decided, okay, it'd be nice to not, because we're comparing against just one project. Let's look at another project and another GCM. So figures 8 and 9, I believe, are my Proxima Centauri B runs. And so so again, these were both, so these were both, I didn't do a dry run with these. I did aqua planets for both of these. So these have water.
Okay.
And I wanted to check against the Turbit et al. Paper for Proxima Centauri. 2016 is the original calculation. Turbit et al. 2016. He used 376 ppms of CO2, 1 bar N2. I just followed his rotation rate and everything.
Composition,
and composition, and this is what I get for that composition. And again, even though the temperature is 254 K, is different from, say, the dry cases we saw earlier, because you're still getting some transport to the night side from the day, a little bit at least, because of the water in there. But again, this is still, it's pretty cold. 254, that's almost 20 degrees below the freezing point of water. So it's not exactly, tropical or anything. It's
subtropicals. There's 8, and now we're gonna do the 1 bar CO2 case. Okay.
Yeah, then this is the really hot case. I think this is the hottest simulation in the paper. So this is the 1 bar CO2 Proxima Centauri B case, also in the Turbit et al. Paper, and
quite a bit.
It's quite a bit warmer. You even the night side is warm. I mean, you're getting temperatures that are well above 290. And the other interesting thing about this is the lack of gradient. So there's little like the difference between the night and day side temperatures are just a few degrees.
Okay, yes.
So you've gotten to a point where you've gotten so warm and your atmosphere is so thick, and the transport is just very good, and it's just it's just almost a homogeneous temperature is what you're getting on this planet. So it's very interesting how this model operates as you vary the composition, the rotation rate, and it can actually do both of these regimes. And so I think another take home money plot. So if you wanted to see how this model compares with 3D GCMs, that's what figure 10's all about as well. So
funny money picture. Okay.
So this is now again, I didn't compare across the whole wide assemble, but I just picked 2 GCMs for different cases.
I'm with you.
And when we look at these models, so I compared against the Rocky 3D GCM and also the LMD model that Turbet et al. 2016 used for top and bottom.
Yes.
Now, the first thing I want to say is the benchmark cases. So these are the dry planets. I definitely did not expect, or at least the top right. And then there's also a present Earth case in the bottom right.
Right.
But in the top right corner, we have benchmark cases 1 and 2 for dry planets. Now, I definitely did not expect the results to agree very well in the dry. This is exactly what I expected. Because this model is actually not, if there's a weakness to the model right now, it'd be great for future work. It's really for habitable, it's really for planets that have at least a little bit of water. Like in the completely dry regime, I had to make some, it's hard to do you don't really understand the diffusive heat transport that well for this regime. I had to use some approximations in the literature. But I mean, conceivably, if you wanted to improve that, you can and get better matches. So the dry cases in the top right, I mean, I did not expect that the model would agree that well with GCMs. But when we look at the habitable cases 1 and 2, Proxima Centauri B and present Earth, the present Earth is a different case now, though. Now this one's not comparing against GCMs, but against observations. So let me just put that caveat. So the other 3 panels are comparing against models, but the bottom right is this model comparing PlayHab, which is, by the way, if I haven't mentioned, it's the planetary habitability model. That's the name. That's what that means, PlayHab. The other 3 panels, yes, I'm comparing against GCMs. Now the left panels are interesting. They show so when we look at the main surface temperatures, they're within a few degrees of the GCMs. Now the other aspect that's important is not just getting the mean surface temperatures correctly, but you're also looking at how the equator to pole temperature gradients vary among models, and they are all also still relatively good. I mean, within the range of, I mean, if you look at across and in some of GCMs, there's going to be a pretty good variation in the gradients itself. So this is again consistent with that. But you do see similar patterns. For instance, the Proxima Centauri B, if we look at the lower left panel, the blue curves, for the 1 bar CO2 case, so that again, this is the figure 9, the really hot planet has a very small temperature gradient. Right. Well, the 3D GCM also gets that, right? So that's the dashed line. They also don't get much of a big difference. I don't understand, though, because one thing that's a little bit puzzling about this, though, is with the LMD model, there is some heterogeneity that's not present in the other models. These are flat plans without topography. So it's a little bit odd to me that I don't quite understand it, but why the LMD model shows this heterogeneity between the northern or
pole equator.
Yeah, the pole equator, this heterogeneity, right, between the northern and southern hemispheres. It's not symmetric is the word I'm looking for. It's not symmetric. And I think it should be. If you look at all the other simulations, even from the other 3D GCMs, are all symmetric. So you have to take that into account as well. But I think overall, they are showing a similar thing that for the that hot Proxima Centauri B case, there's not much of a temperature gradient from equator to pole. And again, the gradients are similar. If you calculate the global mean temperatures and things, they are all very similar to within a few degrees to 10 degrees or so, like a few degrees, like sometimes just bang on. like many times bang on, and other times just a few degrees off or a few degrees different from
I'll take that.
like the GCM model. So it's consistent, and that made me happy.
Sure.
And then table 2 just kind of tabulates everything, or at least some of the main points, the average values for temperature and emission and albedo for the various cases we've discussed in this paper. Just a summary. This is just a summary table of all of that.
Nice.
And
very cool.
Yeah, and we just talked about figure 11 again. Again, this is yet another GCM, and how the gradients from equator to pole for figure 11 are just, they look pretty darn good. And I go through, some discussion, interesting discussion about the kind of slight differences between my model and the GCMs, or, and what they could be. And then the appendix just goes into some more technical details on how certain things were done, and that's really it. That is in a nutshell what the paper's about.
Okay, cool. I would like to point out that the code Playhab is publicly available. You can go check that out. It's there. You can download it.
Yes.
It's ready to compile. So do check that out. I'm a big proponent of open source software.
Oh yeah.
Very nice. Very nice. Ramses, I want to thank you so much for walking us through your very lovely PSJ article. Thank you.
It was a pleasure. Thank you. It was a pleasure talking about it.
Sure. And you hinted at it a little bit there at various points, and so I'll just push on it a little bit. So where do you think we go with this over, let's say, the next couple of years? Or are there additional macro simulations for other planetary systems to do? Could some of the constituent physics in the code be improved? Do you dare apply the EBM to a 3D configuration? Just sort of next steps. Where do we go?
Definitely. I'd love to answer that question. So almost like basically all of the above. As far as improving the model goes, as I also alluded to in the paper, I'm involved in various intercomparison modeling groups. So not just TRAPPIST, but also Fillet and others, the TIE and SIMOS and these other intercomparisons that are going on. We're comparing 3D and simpler models as well. And my goal in those is to learn from the 3D GCMs and vice versa, and how we can improve the physics in these models. The other thing is, yes, eventually what I want to do is couple this to the 1D model. So the 1D model is vertical. So it does the vertical dimension, whereas this model is mostly, it does a little bit of vertical, but mostly it's the latitudinal, longitudinal dimension. So, so then you can couple those and technically get a 3D model. So that is something else that's on my mind.
I think I've heard that called 2.5D before, I think is the phrase.
Yeah, probably that's something like that. Yeah. So that would be the next awesome step with that.
Okay, nice. Good, cool. Well, I will look forward to seeing that development. And I look forward to seeing this software instrument get out there and get used and produce some good science. So very good.
Yes, that's what I'm looking forward to. Thank you. Thank you very much, Frank.
And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.